Hi everyone, welcome back. So in this video, we will discuss about virtual file system in the Linux. So let's get started. So this is the content that I will be discussing in this video. So we will discuss about common file system interface, or we can say that the VFS. Later we will discuss about Unix file system, and then we will discuss various VFS objects and their data structures. So most of the part of this video will be based on the VFS objects and their data structures. So here you can see that this is user space. So whenever user space want to read, write or modify a file, then it execute a system call on the VFS. So user space does not have to worry about what is the uh, behind the scene file system type. It just issues the common system calls to access those files. So it is the responsibility of the VFS to communicate with the different file systems and provide the functionality to the user space. And we will discuss more about in coming slides. So we can say that VFS is the glue that enables system calls like open, read, write to work on any file system and on any physical media. So later we will later in the series we will discuss about block IO layer. So block IO layer and VFS both provides the abstractions, interfaces and different data structures to the user space so that they can use generic system calls to access files on any kind of file system or on any storage media. So on any storage medium means these files can be stored on different kind of storage medium. So here is the view of virtual file system where it exists. So it exists on top of different kind of file systems. So these file systems provide the structures and the operations that is required by the virtual file system. So with the help of those, it provides the functionality to the user space. So as we have already discussed that VFS provide common file model. To support this common file model, it has to provide some the common data structures and the interfaces. So this is the responsibility of the of these file system to provide these abstracted interfaces and data structure to the VFS so that VFS can service the request of user space. So here we can see that the user space does not have to worry about what is the actual implementation of the file operations on each of the file systems, and they can issue the generic system calls to do some operations on the files. So here let's take an example of the write system call. So user space issues the system call into the VFS with the help of the sys underscore write system call. Then this system call is translated into the write method of a specific file system, and then it lead to the write in the disk. So in this way, you can see that this is the actual communication between the user space and the actual file system and the physical media. So here VFS acts as a mediator to help in that process. So let's now discuss about the Unix file systems. So Unix provides 4 abstractions to represent its file system. So first abstraction is files, second is directory entries, or we can say Dentry. And the third one is Inode, and fourth one is mount point. So we will discuss about each of them in coming slides. So you can say that file system is a hierarchical storage of the data, which is adhering to a specific structure or tree. So these file system contains files, directories, or other, in other words, we can say folders, and the other control information or metadata about these files and directories. So most common operations on file systems are creation, deletion, or mounting. So in Unix, file systems are mounted at a specific mount point in a global hierarchy. And this global hierarchy is known as namespace. So namespace is collection of some processes and some global resources. So it enables these processes to see these unique resources. So processes on different namespace can't see these resources, and they would get an illusion that they have this whole data in their space. So in Linux, we mount the file system in the MNT namespace. So let's now discuss the each of the abstractions in the Unix file system. So here the file is an ordered string of bytes. So the first byte marks the beginning of a file, and last bit tells that it is the end of a file. So these files are organized in directories. So directory, we can say that act as a folder, and it contains the files. And these directories can also contain other directories, so we call them as the subdirectories of that particular directory. So as we have seen that the path of a file can be like something sys kernel or something. So here you can see that the each component of this path, like slash sys kernel and all the name heads, these each component is known as the Dentry. So we represent files in Unix file system. So in Unix, control information or metadata of each file is stored in a separate structure, and this structure is known as inode or index node. So this structure contains the access permission of file size, owner, creation time, and many other things. And we have another structure called super block. So this is data structure containing information about a specific file system. So it represents the file system as a whole. So let's see with the help of this example how the Unix file system is. So if you consider the whole box of file, then it represents a file system, and this file system contains multiple files, like this is one file, this is two file, this is third file, this is four file. So like each file is associated with a file name and the inode. So this inode actually contains all the information about this particular file. So this inode tells where is the actual data of this file. So this data is somewhere else in the disk. So this represents the data of a inode, or you can say in other words that it is the data of a file. Actually, the VFS of Linux is based on the Unix file system. So we have a name of the VFS objects as same as the Unix file system. So in VFS, we have 4 objects to represent virtual file system. So first one is super block, second one is inode object, and third one is Dentry object, and fourth one is file object. And these names are same as like the Unix file system. So here question comes, why we don't have the directory object? So in Linux, we represent everything as a file. So directory is also a file. So we don't need to have a specific object for the directory, because we can represent the directory with the help of this file object. So the detail of each of the object we have already discussed in the Unix file system. So these contain the same information. So each of these object inside them has an operation object, and that operation object tells what kind of operations we can do on that specific VFS object. So like we have super underscore operation. This object tells what kind of operations we can operate on the super block object. Similarly, we have inode underscore operations, Dentry underscore operation, file underscore operations. We will see these things in detail in coming slides. And here is some other uh, different structures that is also important for VFS file system. So we will discuss about these in coming slides. So let's now discuss super block object. So super block, or we can call it as the control block, it is stored in a spatial sector of a disk, and we will see where it is stored. So we have some file systems like sysfs that is not based on the disk file system. So when we create sysfs file system, then we create the super block on the go when we create the sysfs. So let's see the view of the actual disk where these structures are stored. So here you can see that this is a specific sector of disk where superblock is stored, and it also contains inode structures. So these two structures or objects are stored on the actual disk. So let's see different members of superblock structure. So this is the pointer to a list of other superblocks in the file system. This is the size of the block in the bytes, in the bits, and this is the flag to say if the superblock is dirty, means we have modified something. And this is the main structure that we have already discussed. So this is the superblock operations, and it contains the pointers to the different functions that we can operate on the with the help of superblock object. And we have different other important fields, like this is the entry to the mount point directory of the file system. So here we have the list of all the inodes associated with this specific file system, and we have dirty inodes, and this is the write back list of write backs, means these changes we have to flush back into the disk. And similarly we have different kind of members in this structure depending on the requirement of the file system. So when we create or we mount a file system in the Linux or in the virtual file system, then this alloc super function is invoked, and it creates the VFS superblock object from taking data from the disk and populating it. So let's now discuss the superblock super underscore operations. So as we have already seen, this is represented with this structure super underscore operations. So here it is telling some important things, so we have to read it carefully. So it is saying that super block operations perform low level operations on the file system and its inodes. So in the next slide we will see how it is doing operations on the inode. So if we want to apply specific operation, then we can access that operation with the help of this structure, and within that structure you can point to that specific function. So here is the structure of super underscore operations. So here you can see these are the function pointers to different functions depending on the functionality of the functionality provided to the super block. So here, like this alloc inode creates the iloc creates and allocate the inode in this specific super block, and this destroy inode deallocates the inode structure, and this function is called when we have some changes on the specific inode, and this function write inode is invoked when we write the data on inode structure to the disk inode structure. Similarly, we have drop inode. So when the reference to this inode is reference to this inode is dropped, like the reference to this inode is 0, then this function is being is invoked. So generally this drop underscore inode function deletes the inode. So this is delete inode function. So this actually deletes the on disk inode structure from the disk. And when we unmount a file system, then this structure put super removes the super block structure from the file system. And similarly, we have this sync fs function. So it syncs the super block metadata or the file system metadata to the disk super block. And similarly, when we want to change the mount point of a file system, then we run this function to change the mount point of a mounted file system. So let's now discuss the most important object of a file system, that is called as the inode. And here let's see, this is important statement. So it says the inode object represents all the information needed by kernel to manipulate a file or a directory. So here, as it is saying, it is containing all the information to manipulate file or directory. So in coming slide, we will see that its operation specify the operations for files or directory. So here, this is the another important statement. So it is saying inode represents each file on a file system. So you can say that every file on a file system has file name and associated inode. So this is true for every file, and file can be regular file, or file can be a directory, or file can be device file. We will see each of these things in coming slides. So here is the layout of the inode structure. So it contains some control information like order, group, mode, flags, timestamp, and hard links, soft links. And at the end, it contains the block pointers to the actual data on the disk. So it contains three kind of pointers to the block pointers. First is direct, second one is indirect, and third one is doubly indirect. So it depends on the size of the inode. So depending on, we can have indirect blocks or double indirect blocks. When we have large structure, then generally we have double indirect blocks. Generally we have direct blocks and indirect blocks. So this is the structure of inode. So here you can see this is the list of other inodes. Each file is associated with the inode. So each D entry, this is the list of each D entry, and this is the inode number, and this is the count that, so like multiple files can be associated with a specific inode. So it tells the number, how many files are associated with that particular inode. And this, as we have discussed, this is the id of the owner, this is the group id of the owner, and this is the size of the file in the bytes. So here, as we have discussed that uh, inode and inode represents the actual data of the file. So when we access file, modify file and delete file, so at that time we store the timestamp. So it is having those members to represent those time, like access or modify time. So here you can see it is representing access time, modify time, change time, and these are the logs and permissions. And here we have the structure inode of. So this structure is telling what kind of inode operations we can do on a particular inode structure. And this is the pointer to the super block on which it is associated. So here you can see, as I have already mentioned, that we can represent the, in Linux we can represent everything as file. So this inode contains this union. So it contains like pipe, block drive, block device, character device. So these pointers represents uh, the device files, devices as file. So with the help of these structures, we can represent devices as file, and we can store their information in the inode structure. So let's now discuss the inode operations. So similar to super underscore I operations, we have inode underscore operations. So here it is also the pointers to the functions. So this create pointer is, create function is invoked when we start a open or create system calls. At that time it creates this d entry and associated inode, and this is lookup function. So we have to match the inode number with this given d entry. We have to return that d entry. So this is the link function. So in this is invoked when we call the link system call. So in this function it will create a hard link to that, to this particular d entry and this particular inode, and it will link to this d entry. So like this d entry will be representing the hard link of this d entry which is associated with this inode. Similarly, we have unlink function. So it will unlink a particular link that is represented with the help of d entry. Similarly, this is function to create the symlink, and this function is for making a directory. This function is for removing a directory, and this mk node function is to make the node of a device file, and this is to rename a d entry, and this is to read the link. Link means we have to read this d entry object into this given character buffer, and this is the length of length variable. So these we have to read the information into this buffer. Similarly, we have this truncate function. So truncate function tries to like change the length of a file. So we have to update the length in the inode, and then accordingly we can change the length of the file. And this function permissions check if the access permissions are available on a particular file or not. If the permissions are available, then we return 0, otherwise we return non-zero. And we have some other functions according to the requirement that we do with the help of inode operations. So let's now discuss the soft link and hard link. So let's now discuss how soft links and hard links are created. So here in the left of this slide, you can see that this file name bar.txt is associated with the inode number 23456. So this inode is represented by this structure. So here you can see that this foo.txt file is associated uh, with some other inode, and within this inode we are updating the soft link as the link to this inode. That means it is a soft link because this inode represents some other inode. And here in the right of the slide, you can see that we are directly pointing this inode to the this inode. That means this is a hard link. And this is the, it is showing that how we are representing the actual data on the disk with the help of disk block locations. So let's now discuss the dentry object. As we have already discussed that dentry objects are the all components in a path including files, and it can also includes mount point as well. So here, like we have the example, this path. So dentry object will be slash bin and vi. So here these two dentries are directories, but this is a regular file. So the dentry object can represent a directory and file and the mount point, and this file can be of including devices. So this is the structure of dentry. So here you can see the required information. So like dentry represents the entry of a like a component in the path. So like take an example here. So like we have this bin or foo. So here you can see that if these are the directories, then it has to contain the information of child so that it can know where it is, from where it is coming, and uh, uh, sorry, the child, so where it is going, and the parents from where it is coming. So this information we can find here. So like from this entry we can say what is the parent of this d entry, and we have also the this object. So here we can see what is the list of the d entry inside this particular d entry, so that this is the, and this is the, these all are the childrens of that particular d entry. So these and d entries can be directories or can be file depending on the situation. And this is the associated inode with that particular d entry, and this is the usage count, how many files are using this particular d entry or process are using this d entry. And here you can see the d entry operations object. So it contains all the functions and that we can invoke with the help of this d entry object, and this is the pointer to the super block of this particular file system. So let's now discuss the d entry state. So d entry can be used, unused, and negative. So in the used state, the d entry is associated with a valid inode. Here we can say valid inode. So that means currently some process is using that particular d entry or file, and it is associated with a specific valid inode. And when it is unused, that means it is associated with a valid inode, but currently not being used. Here currently being used. And in the negative case, when it is uh, not valid inode, so it is not associated with any inode, so we keep it as a negative value, so that when we are searching for that particular D entry, then we can get that value that it is not associated. So like we have to uh, parse the path whenever we want to search for a specific file. So this is a time consuming task if we are doing again and again. Like we have some operations where we have to access a particular file again and again. So for that optimization, we have something called as the d entry cache, where we cache the d entry object with the help of a hash table. So we call that hash table as the d-entry hash table. So this d-entry cache is consist of used d-entries. So it is a list of list and their associated inodes, which d-entries are currently in used. And this is the least recently used list where we contains unused and negative d-entries. So we have already discussed what is used and negative entries in previous slide, and similarly we have discussed where what is used entries. And third is it contains the hash table and the hashing function. So this hashing function ensures that for each entry component, it calculates a hash and it stores in the hash table. So we search the hash table with the help of this d lookup hash function. So here is the d entry operations. So it is also the pointers to the functions. So when we are accessing the d entry cache for a specific file, before that we try to validate if this d entry is valid or not. So for that purpose, we invoke this function. When we are storing the d entry value in the d entry cache, then with the help of this d underscore hash function, we try to calculate the hash value of that particular d entry. And this is the comparison function to compare two strings representing the d entry, and this is generally the string comparison. And this d underscore deletes the d entry, and this d underscore I put function is being called or invoked when this d entry is not associated with this inode. So let's now discuss the file object. So file object represents a file that is opened by a process, and this file object represents a open file in the memory. So when we open a file with the help of this open system call, then this structure is created and it is stored in the RAM. And this structure is destroyed when we call close system call on a particular file. So this file object is represented with the help of this struct file. So here we can say that we can see that it is saying that this file object is associated with a inode. So it is associated with the inode with the help of d entry. So you can say file object is to d entry, and then it associates to inode. So in this way we can see again that every file is associated with a particular inode. So here is the actual structure of file. So here you can see this is the D entry for that specific file, and this is the structure to the file operations that we can do with the help of uh, this file operations structure. And this is the count of the file used by different processes, and this is the data owner for signals, and these are the access modes, like we specify if we are opening file in the read mode or write mode or both. And this is the log to uh, secure from concurrent access to this file object. So these are the file operations. So here you can see this is lseek, read, write, and asynchronous IO underscore read. So these functions are actually invoked with the associated system call. So when we invoke the lseek system call, then this function is being called. And similarly, we can have this ioctl function. So with the help of this function, we are trying to give the command and the arguments to a specific device file. So this ioctl is for file operation for a specific device file. And similarly, we have compat underscore ioctl. So this is used by applications which are running in the 64-bit systems, but those applications cases were for 32-bit systems. And similarly, we have this open pointer function, and it runs when we invoke a open system call to open a particular file. And this is the fsync function. So we are trying to sync the file object data to the disk. And similarly, we have some other different functions. So let's now get the overall view of different structures. So every task or process in a system is represented with the help of this task under this struct. So in this struct, we have files struct object. So it contains this table of uh, file descriptors. So this file descriptors tells what are the different open files uh, for that particular process. And these, as we have already discussed, that each file is associated with a D entry, and in turn D entries represents to a specific inode, and those inodes are associated with a specific uh, super block for that particular file system, and then it goes to the disk. So here you can see all these VFS objects are useful when we are running some process in the system. So let's now discuss two structures, and this file underscore system underscore type and this struct VFS mount. So these two structures or objects are specific for a specific file system. So this file underscore system type tells what kind of file system it is and the associated information about its capabilities and behavior of the file system. But this VFS mount structure represents a specific instance of a file system. Means it is telling that it is a mount point for that particular file system. So let's now discuss file underscore system underscore type structure. So here you can see this is the name of the file system, and this is the function that we invoke uh, when we create a when we mount a specific file system to read the disk superblock structure. And similarly, we have the owner, uh, and then we have the link to the other file systems in the system. And then we have some other information. Now let's see the VFS mount structure. So here you can see that as we have already discussed that in the system uh, we are separating different resources with the help of namespaces. So here you can see this tells this this mount point is associated with a specific namespace, and it tells the parent mount point of that particular file system, and this is the D entry for that particular uh, mount point, because we can also represent, as we have already discussed, that we can represent the mount point in the D entry. And we have some other very members depending on the requirement of this VFS mount structure. So let's now discuss the data structures especially associated with a process. So as I have already told you about this files underscore structure. So this all these structures are part of the process descriptor of a particular process. So in this way, we can say that these are specific structures for particular process because they are represented in the process descriptor. So this is files underscore struct structure. So here you can see this structure tells all the open files and file descriptors associated with a process. Here you can see this count variable tells the count of usage of this files struct, and here you can see this is the struct of type file. So this table keeps the entry of all the files opened by a process. So this is default like 64 processes. So when a process is opening files more than 64, then it again creates this kind of table, and the newly created table is pointed by this FDT table pointer, and this represents the base FD table for this specific process. And this entry tells what is the uh, next cache entry of a file descriptor. And this is the fs underscore struct structure. So this structure actually keeps the file system specific information related to a particular process. So here you can see it keeps the root path to the root directory, path to the current working directory or present directory, and here it is setting if this file is being executed or not, and this is the usage count of that particular structure. Here it is the namespace structure for a particular process. So this namespace represents that this particular process have access to particular resources of the system. So here you can see this is the pointer to the mount point or the root directory where it is, where our file system is mounted, and here is the list of all the other mount points so that it can see the different file system associated uh, in the system. And this is the list of mount points in this specific namespace. So like we can have different file systems in a particular namespace, so each file systems will be sharing the same namespace. So in conclusion, we can say that we have discussed different data structures associated with the VFS file system. So we have discussed the Unix abstractions to the file systems, uh, and based on the abstractions provided by the Unix file system, we have discussed the VFS file system. So we have discussed inode, dentry, superblock, and file object. So this is all for this video. I will see you in the next video.